So as you will soon learn, he's a very diversely talented and knowledgeable physicist. I just got the rundown on his early career, which was he was a graduate student at Stony Brook and then went to INT in Seattle, then MIT, where he and Roger Gopal and Wilczek worked on color superconductivity. And then he went to Los Alamos and was a faculty, sort of faculty there, and then got lured to INT, where he's been back to Seattle. And he's now the director of the Institute for Nuclear Theory. And well, I will quit talking so you can start. But I have to say an important thing, which is that his daughter is a sophomore at NYU. So we can lure him here with regularity if you wish. So.
Thank you so much. Thank you for your kind words and also for hosting me and for entertaining a talk about nuclear physics. I realized after I sent you the title that the word neutron star should have been there, but it's missing. But you will very quickly see that what motivates me most of the time is not nuclei, but neutron stars. So let me begin by just giving.
Please don't let me out of
Some kind of it working.
Yes, you click your screen first, though.
I don't know if other people have that reaction, but.
Okay. Yeah, but not through the remote.
Just in there.
Oh, okay.
Oh, there we go. Works good. I just thought.
Okay,
See it has.
but it's not moving on Zoom. What's going on?
Maybe sharing your screen.
Okay, there's a lag. Okay, let's not worry about it. It's fine. I'm done. Okay, so the plan of my talk is to give you an introduction to both nuclear interactions and neutron stars, and then talk about how we are trying to describe the dense matter that occurs, at least in the outer regions of the neutron star, and mention two recent results. One has to do with a new class of 3 nucleon forces, and I'll motivate why the force between 3 nucleons is so important for neutron stars along the way. And then I hope I have time to talk about the condensation of QCD axions inside neutron stars. And if you're interested in learning about it, there are papers on the archive that you can look up for both these topics that are new. Okay. So just in a nutshell, what is nuclear physics doing these days? They're basically working on dense matter in 3 different contexts. In the first field of the structure of a nucleon, we're trying to understand what's going on inside a single hadron. How do quarks and gluons come together to give you the masses and the properties of single hadrons? And in low energy nuclear physics, we are trying to understand how these nuclei or hadrons interact with each other and form nuclei and all the structure that follows. To some extent, this is, like a 40, 50-year-old subject, but there have been recent developments that, put some of these studies on firm grounds. And the same physics that influences what's going on inside a nucleon and inside nuclei influences a very large region of the neutron star. And the question is, can we make quantitative predictions using nuclei as laboratories to study neutron stars? Okay. And the reason all of this is interesting, neutron stars have been around since the late 1960s, and they've been around in the world of theoretical physics for almost 100 years. But measuring properties of neutron stars have been incredibly difficult, simply because there's a lot of interesting plasma physics that intervenes between what you see and what you really want to know about the interiors of neutron stars. But there's reason to be excited because gravitational wave astronomy is making important strides in measuring properties of the neutron star that are intrinsic properties of the star itself, not so much about what's happening at the surface, but what is the mass of the neutron star, what is its tidal deformability, what's its radius. These sorts of measurements can be made in a very clean way if we observe neutron star binaries using gravitational wave detectors, such as the ones that are shown here. In addition to the two detectors here in the United States and one in Europe, there's going to be a new instrument in India, in Japan. And the real excitement is going to probably start in the 2030s when we have next generation ground-based gravitational wave detectors, one being planned in Europe called Einstein Telescope, and another one in the US called Cosmic Explorer. And these are expected to be about 10 times more sensitive than what we have. And this factor of 10 is pretty much revolutionary when it comes to studying neutron stars. And the reason it's a big deal is because if you think about the reach of these new detectors, basically when they go operational, let's say in the next 15 years, gravitational wave astronomy, these new detectors will detect all of the neutron star mergers in the universe. Okay, so every single merger, and this is a beautiful map that's in the science book put together for Cosmic Explorer. This is the reach in redshift. They go all the way back to redshift of 10. So your event rates are going to be staggering once you get to this next generation gravitational wave detector. Okay, so right now we see maybe one neutron star merger a year, but Cosmic Explorer, and see, this is the neutron star merger that we saw, very close, just 40 megaparsecs away. And this is where the big population exists. And once you go past that distance scale, your event rates are going to be something between 20,000 and 100,000 per year. So people have conferences on how to deal with two events in your detector at the same time. So that's a good problem to have, but it's not going to be, a major issue until we build these detectors and we see tens of thousands of neutron stars. A small fraction of these will be close enough so that the signal to noise in the neutron star merger dynamics will be adequate to make precise measurements of the neutron star masses and their radii. In fact, what is measured is something known as the tidal deformability, which is how much deformation is there when the neutron stars are close in a closed binary. But from that, we can deduce the neutron star radius. So the hope is that we'll know masses and radii for neutron stars in the tens or maybe hundreds sometime in the mid 2030s. Okay, and if they're very close by, then it turns out that we can also study what happens. This is a beautiful animation that many of you may have seen already, but it just shows that the neutron star merger, this phase is when you measure the radius, but post-merger, the ringing of the neutron star that ejects a lot of that material, that dynamics on a 50 kilometer times scale can imprint on the gravitational waves as well. So we may be able to actually have some idea of what sort of hydrodynamic motion is at play after the merger. And so for those sorts of events, we need to be very lucky, actually. So this motivates the study of neutron stars in a coming decade, where we want to make some definitive statements about the neutron star interior by measuring the masses and radii of neutron stars. So the simplest, if a neutron star is not rotating very rapidly, then there is a simple relation between the pressure and energy density, which is called the equation of state of matter, and the mass and radius of a neutron star that you measure. So this is what we would like to know. These are densities that are significantly higher than the density inside a nucleus. So you can think about, typical densities here would be 10 to the 14 to 10 to the 15 grams per centimeter cube. And the mass and radius. So this unique relation, once you specify the pressure as a function of energy density, it uniquely predicts the mass radius curve. So the holy grail of neutron star science for many years was, let's measure a bunch of neutron star masses and radii and then infer the pressure energy density. And that was not particularly successful because the errors associated with these measurements were too large. And so, doing the inverse problem of going from mass radius to pressure energy density has not been very successful. But there are some trends that you can extract already from asking about, how do different curves on the pressure energy density produce different curves on the mass radius curve. So for example, if you look at the yellow curve here, it has low pressure and high pressure at high densities. They tend to make neutron stars that are smaller, but have a much larger maximum mass. So all neutron stars have a maximum mass above which they will collapse to form a black hole. So if you have an equation of state that is very stiff, which means it has a very high pressure at high density, then it tends to make larger maximum masses. So we already are beginning to get hints that the neutron star radius is rather small from the gravitational wave observations of GW17 or 817. We already know that the neutron star radius cannot be too big. The constraints on amount of deformation during the merger poses a limit on the radius. We've also measured neutron stars with masses that are larger than 2 solar masses. Okay, that was a little bit of a surprise to nuclear physicists because it isn't easy to make equations of state that can support 2 solar masses as heavy as 2 solar masses.
Is there such a thing as a minimal neutron star mass?
Yes, there is a minimal neutron star mass. It's about 0.25 solar masses. Beyond that, it tends to just become a white dwarf.
But supposedly we cannot produce those.
Yeah. Right. So if we see in LIGO band, if we see an object that is less than a solar mass, it would be really puzzling for stellar physics because we don't know how to make such objects. Only white dwarfs exist in that range, and white dwarfs are not in the LIGO band. So even just seeing something odd in LIGO in terms of mass would already be a major discovery. As a side point, yes.
Sanjay, I'm confused about something very basic. I'm confused about the non-function on the right there. Let's say the yellow curve. Close to the peak, it looks like for a given mass, there's 2 values of radii. Is one stable, the other unstable?
Exactly.
Okay.
But there are even 3.
Yeah.
Yes.
Or at one radius, there's 3 masses, but at one mass, it looks like there's 2
Right.
radius.
So once you go past the maximum, there is a unstable point. Right. But if at a single radius you can find two mass stars, that's fine. They just have very different internal structure.
But they are both stable.
They're both stable. The stability, I mean, in general, the stability analysis shows that anything to the left of the maximum is unstable to radial oscillations. There could be other instabilities that are also studied.
Here, how is it relevant whether neutron star is rotating or not, the spin of neutron star?
Right, then it'll change the curve. If you're close to breakup, then you can support up to say 3.5 solar masses. So you have to spin the neutron star very close to breakup to actually change these curves. And there are very few neutron stars that are spinning so rapidly. But after the merger, when you merge the 2 neutron stars, that object is spinning rapidly, and there you have to worry about rotation.
And from the gravitational wave observation, one can also determine this.
The neutron stars that are merging, we expect to be non-spinning because they're very, very old and they would have spun down by dipole radiation.
Yeah, if I heard you right, you said we should think about anything to the left in radius of the maximum is unstable. So at least for this yellow curve, that means there's a gap in the mass spectrum. There's some range of masses where nothing is.
So everything to the,
You mean to the left on the line or to the left, literally you draw a vertical line down?
yeah, if I draw a vertical line at the maximum, everything to the left of that region is unstable.
Only in the top or also in the section?
No, this is stable.
That's stable, okay.
Yeah. So as long as the central density keeps increasing, you're stable. Okay, so this motivates us to predict neutron star mass radius from theory. And so this is a field that, has been around for several decades. And the reason it's a difficult object to study is it's only a part of the neutron star that we can describe using controllable theory. And the reason is that the density increases very rapidly. So this is like a theorist's view of what the interior of a neutron star looks like. Until about a few times 10 to the 14 grams per centimeter cube, neutrons and protons are good degrees of freedom. We can think about there being an actual separation between neutrons and protons. But once you get to the point where the interparticle separation becomes comparable to the size of the nucleon itself, then describing matter in terms of neutrons and protons is not useful, and it's very hard. And that's the region where we call there should be a quark hadron transition, where the quark degrees of freedom inside a nucleon actually becomes important. And maybe we reach a stage where, quark matter itself is fairly well ordered. And there are many suggestions about, maybe a color superconducting phase of quark matter. So unfortunately, we have lots of beautiful models for this, but we don't have good, reliable techniques to calculate things like pressure.
Is it so it's completely established that it's superfluid, the neutrons are superfluid in the outer crust?
Yeah, there is lots of observational evidence for superfluidity in the outer regions of the crust. That's a whole nother talk, but I'm happy to chat with you later.
Or come back, give a talk.
Yeah. So, if I want to put everything we know about the equation of state on one slide, this is now over many orders of magnitude. At low densities in the outer regions of the neutron star, we know the equation of state very well because the pressure is dominated by relativistic electrons, okay? And relativistic electrons, we know how to calculate the pressure of relativistic electrons without any approximations. And as you start getting to higher densities, at some point, you start dripping neutrons out of nuclei. So here you have relativistic electrons in nuclei, and at some point, the neutrons start coming out of nuclei. And in addition to relativistic electrons, you have a gas of neutrons. And this gas of neutrons is dilute enough that we can again do nuclear physics calculations with low enough error bars until you get to about nuclear densities. And when you get to nuclear densities, the interaction energy of neutron interactions become very important. And then we start having uncertainties in the predictions for the pressure. And these uncertainties grow very rapidly because we have an effective field theory to describe these interactions. And the breakdown scale of the effective field theory, as I'll describe in the next slide, is around this density. So when the density is about 2 times the density inside a nucleus, the theories that we currently have to describe nuclear interactions come with very large error bars. And so at some point, you just can't use that theory anymore. And that's the red line that divides what you can calculate from what we have to speculate using models. And interestingly, if you go to very high density, like 40 or 50 times the density inside a nucleus, again, life becomes easy because perturbative QCD applies at very high chemical potentials. QCD is perturbative because of asymptotic freedom. And you can do a calculation and assign an error to the pressure of matter at these very high densities. Unfortunately, most of the neutron star lives in this region, right? So we can still make some progress using 2 very simple principles. The first principle is that causality should be obeyed by neutron stars. That means that the speed of sound inside a neutron star cannot exceed the speed of light. And the derivative of the pressure with respect to energy density is just the ratio of the speed of sound to the speed of light. So by restricting all equations of state to lie below this, you're imposing causality on the neutron star. And we've seen neutron stars that are more massive than 2 times the mass of the sun. So what that means is that you need a minimum pressure to produce a 2 solar mass neutron star. So in this region where we cannot calculate, we have very interesting boundaries. Boundaries coming from causality that says you cannot arbitrarily increase the pressure because at some point you'll violate causality. And a lower boundary saying that if your pressure is too low, you will never be able to construct a neutron star that has 2 solar masses. So now, in this region where we are speculating, we have useful guidelines for what to do with the equation of state.
Shouldn't this law approach 1/3 as you go to the perturbative QCD?
So we think that when you go to perturbative QCD, it has to go back to 1/3. What's interesting is that neutron stars are already telling us that the sound speed is not a monotonic function of density. So in fact, that's one of the new, I would say, breakthrough insights from neutron star observations is that unlike at finite temperature, where the speed of sound is a monotonic function, it never exceeds 1/3. At finite density, it does have to exceed 1/3, but it'll come back later. that turns out to be a useful constraint for building equations of state. So coming back to low density nuclear matter, I said that there's been progress in trying to calculate the role of nuclear interactions. And this progress comes in the form of effective field theory. In the old days, people would write down a Schrodinger equation for nucleons, assign some potential that will fit all the data, and they would say this is a good description of nuclear interactions. But starting with the work of Steven Weinberg and many people since then in the 90s, they reorganized the nuclear Hamiltonian in a power series of dimension of the operator over some breakdown scale. So essentially what they did was they said we can compute forces in a more systematic way so that we can account for the uncertainties associated with unknown short distance physics. And at leading order in this theory, there's just a contact interaction and pion exchange. As you go to higher order in this effective field theory, you get multi-pion exchanges and more complicated contact interactions and so on. But the beauty of EFT is that you can estimate the error and you can also estimate when is this theory
Is
breaking
it the
down.
theory of neutrons and protons?
This is the theory of neutrons and protons. So every time you see this line, it's a neutron and proton. When you see a dashed line, that's a pion. And anything else is just a local operator whose coefficient you're going to fit to data. Okay. And so what that really does is allows you to write down a theory consistently in which pions are accounted for explicitly, because the pion mass is very small. You have to account for the pion dynamics explicitly. But any other dynamics that happens at shorter scales is very high energy physics compared to the scale of the nucleus. So typically heavier mesons in the theory will have masses like 800 MeV. So those don't need to be resolved, and you can just account for that physics systematically in terms of these local operators. So the price you pay, of course, is that this is a momentum expansion. And if the breakdown scale, we find that the breakdown scale is about 500 MeV, which corresponds to about 2 times nuclear density, which means that this theory can only work up to a certain density, maybe twice nuclear density. Okay. But the good news is that we can start asking questions like, what are 3 nucleon forces? When does that become important? And so, for example, in a neutron star, it was considered that this force between 3 neutrons is particularly important, in which 3 neutrons basically exchange 2 pions between them. These other forces cannot operate between neutrons, which is very interesting, because this doesn't work because of the Pauli principle. You can't have 3 neutrons at the same point. This doesn't work because pions only couple to spin, and when 2 nucleons are at the same point, there must be spin 0. So for some number of years, we thought we had a good handle on calculating the properties of neutron matter because there was only one 3 nucleon force. Everything else, which has to do with 2 nucleons, we measured very accurately. So this is all measured in the laboratory very accurately, and there was only one 3 nucleon force that could be understood well, again, from nuclear physics. But what I'm going to tell you, unfortunately, is that this story, which we've liked very much for about a decade, seems incomplete, and that's the first part of my story. And before I get to it, here are various calculations done over the last 10 years using this framework developed by Weinberg, where you can calculate the energy as a function of density. So typically nuclear saturation density is at a density of 0.16 nucleons per Fermi cube. And this is matter containing equal numbers of neutrons and protons. We call it nuclear matter. And if it has just neutrons, we call it neutron matter. And nuclear matter, of course, has negative energy per particle. It's just bound. And the negative energy per particle is bound with about minus 16 MeV. And you can see that the theory actually does reasonably well. So as you go to higher and higher orders in the expansion, you start realizing that you get closer and closer to the empirical point that's been measured. We don't measure neutron matter, so this is all predictions. This is the only empirical point in this graph. And the second feature that I want you to recognize is that the three nucleon forces appear at this order, which is called N2LO, and they are essential for increasing the energy. Increasing energy with density means repulsive forces. So a lot of the repulsive force in nuclear matter and neutron matter comes from these three nucleon forces, right? And that's why this is especially important for neutron stars, because we need that repulsion to make massive neutron stars. The other point to take away from this is, there's a lot of people working hard on estimating the errors associated with this EFT expansion. Yes.
Does this EFT expansion take into account the just for some fact that two protons are positively charged, or is that negligible at these?
Right. So electromagnetic interactions are negligible here. I mean, of course, first, it's electrically neutral matter. So there's a background of electrons always present. Yeah. But the proton-proton Coulomb interaction is very small compared to a strong interaction. Strong interactions are MeV, tens of MeV. The Coulomb interaction is keV at most.
Okay.
So here's, for example, a calculation that I was involved in, which was largely led by young people, Christian, Sophia, and Tianki, who were at that time postdocs. And we came up with the best possible pressure density curve. And then we said, let's use this to build some neutron stars. And what happened was we were able to construct neutron stars using information coming entirely from theory, but only up to twice nuclear density. So if I try to build neutron stars with information about the pressure up to twice nuclear density, I make very small neutron stars, not small, but very light neutron stars, because their interior densities can only go up to twice nuclear density. So I can't even make a 1.4 solar mass neutron star if I terminate the central density at twice nuclear density. So our knowledge of nuclear physics can only allow us to populate this region of the mass radius diagram, okay? If you want to start populating neutron stars here, you need to access higher density. So what we did was we said there are only two possibilities. The highest pressure you can build is by having the speed of sound equal to the speed of light. So if you set the speed of sound equal to the speed of light, that produces the maximum radius for any given mass. So you will not be able to reach radii larger than what is predicted by the curve, because accessing this region will require some part of the neutron star to violate causality. And you can do the same thing, ask, what is the minimum radius I can produce? But I need to be able to produce a minimum radius, but still manage to make a neutron star that is neutron stars that we observe. So the most compact neutron star that we can produce that is consistent with nuclear physics knowledge is given by this. So we can now convert our understanding of neutron stars into bounds, which basically say, if we make predictions up to twice nuclear density, we can translate that into bounds on the radius. Yes, the question.
But I was apologizing for the delay, but I'm asking, this first curve seems to be a natural continuation of the nuclear forces, while your artificial thing with two solar masses produces a break. Doesn't it prove that your first approach is better?
No, this approach is giving me the maximum radius.
Right, but it seems to be a nice continuation of what you have computed from first principles.
Right, that's because, yeah, that's a good point. What is a continuation means that the pressure continues to increase as the density increases. And that, if you ignore first order phase transitions, this is that continuity, the discontinuity of a first order phase transition is what is making this curve look unnatural to you. So this curve is generated by having a very large first order phase transition, right? If you want to make a very small neutron star, you want to have a region that is very soft. You need to be able to compress matter to very high densities. So this curve has no phase transition. This curve has a very large first order phase transition.
But do you expect a phase transition?
We don't, but we want to be agnostic. So I want to develop model independent bounds on the radius of a neutron star. So the smallest radius requires me to have a first order phase transition.
With
Yes,
the speed of
is there a
sound
question?
is, this means the speed of sound is close to the speed of light at the boundary of what you can compute.
So this region has a speed of sound that
No,
is,
no, sorry, I'm asking about the part that you computed.
Yeah.
The fact that it's smoother, the transition, the speed of
so
sound.
everywhere here, the speed of sound is equal to the speed of light.
Yeah, but in the region that you computed, the one before, the corner,
In this region,
yes, what's the speed of
the
sound?
speed of sound at most is about 0.06. At twice nuclear density, you're not even close to 1/3.
Okay, but it's still relative, still very relative.
It's marginally relativistic. Okay, so C is still a good expansion parameter. If C is not a good expansion parameter, the EFT also breaks down. But it also turns out that if tomorrow somebody observes a neutron star that is 2.6 solar masses, then this lower bound quickly starts approaching the upper bound. So if we tomorrow measure a 2.6 solar mass neutron star, even without knowing anything about high density matter, you can be pretty certain that all neutron stars in the universe must lie in this very narrow window. Okay, because that's the only way in which you can construct a neutron star that's 2.6 solar masses and respect causality. So this uncertainty about high density equation of state does not fully limit us from making useful predictions for astrophysics if in fact very heavy neutron stars exist in nature.
I think I recall there's a candidate binary neutron star merger that needs a 3.2 solar
Right.
mass or something. That's
Right, if we take that seriously, then nuclear physics would predict that all neutron stars should have radius of about 12 kilometers plus or minus 0.5, which would be quite remarkable. But we still don't have evidence that that isn't in fact a neutron star.
Can I just a naive person, when you say this is the only way this could happen, I mean, you're allowing things like one first order phase transition. You had multiple first order phase transitions or something.
But if you had multiple first order phase transitions, you end up making less compact stars. So the most compact star you can make is by going from what is currently known about the pressure energy density curve, stick in the largest first order phase transition that you can, and then have a segment in the equation of state that has speed of sound equals speed of light. So this is how you define the most compact configuration. Any other configuration can be shown to be larger. So if I put all of this back in one plot and now add observations to it, this is what we see at the moment. Okay, so we have from GW 1708, the first neutron star merger, we have a measurement of the neutron star radius for a star that's a little bit less than 1.4 solar masses. There's an X-ray observatory called NICER that has been used to measure the radius of two neutron stars, one with a mass of close to 2 solar masses. And there are two different groups that analyze this data, and this is their results for it. And essentially what this is suggesting is, if we take the data at face value, that the data seems to favor a stiff equation of state where the speed of sound is close to the speed of light. Okay, and quite frankly, that's a major challenge for nuclear physics and for high density physics, because generating speed of sound greater than 1/3 is not easy in any field theory or in any approach to strongly interacting matter. So if it is true, this is very fascinating. Okay, but these error bars are, I think, rather disappointing, because these are still 1 sigma error bars, and there are a lot of systematics. It's only the gravitational wave error bar that is something I'm willing to believe. But in the 2030s, if you make a 10% measurement of a neutron star radius or a few percent measurement of a neutron star measurement using Cosmic Explorer, these are the sorts of points we're going to have in the 2030s. Okay, so we are not very far away from pinning down the equation of state, because we are looking in the future for error bars that are going to be significantly smaller. And you had a question back there.
So here, the plot for the theory and those observations for NICERs are mostly considering like low rotations, right?
Yeah, they do correct for rotation. The NICER extraction that's a rotating neutron star. It doesn't affect the mass radius significantly, but it affects their analysis because they're looking at a hot spot on the neutron star. I don't have time to go into details about how they extract the radius, but it's actually a very interesting piece of physics. Okay, so I'm obviously, maybe doing this, going at a pace that's too slow to cover everything I promised. But now to the part where, the nuclear interactions that we thought was so well defined by the effective theory may not be so well defined, because some of the ways in which we were thinking about nuclear three-body forces were not complete. So that's the part of the story that I hope I can tell you in the next 15-20 minutes. So ultimately, we want to derive nuclear physics from QCD. Okay? And what does that mean? It just means that the QCD is such a simple theory. It has just a few parameters in it. It has a coupling constant. It has a bunch of quark masses. And people who think about axions will think that there's another term, which I'll talk about in just a minute. So the coupling constant, we know that it increases with decreasing energy, and that's why nuclear interactions are strong at low energy and weak at high energies. The quark masses, the only quark masses that are typically relevant are the light quark masses. The up and down quark masses are the ones that play a dominant role in low energy nuclear physics. The strange quark could play a role in the neutron stars, and its mass is about 100 MeV, and its role in low energy nuclear physics is not dominant. And the heavier quarks are not of interest to neutron star physics because their masses are significantly higher than the chemical potentials that are reached inside the neutron star. And the other parameter of QCD is this theta parameter, which is related to axions. And this theta parameter we know from measurements of the neutron dipole moment, electric dipole moment, that it is very, very small. But it is the source of all CP violation if I write this Lagrangian in this way, where the quarks have real values. And the fact that theta is very small has been puzzling and has led to many interesting suggestions, including the axion. So can we develop a theory of nuclear interactions which can connect back to the parameters that enter the Lagrangian, in particular, the quark masses and the theta term? So that's going to be the main part of my talk, because the theta term and the quark mass term are in fact related, as I will show later. So the first question we can ask is, if we change the quark masses, what happens to nuclear physics? Okay, the quark masses of the up and down quarks, we know that the pion mass is proportional, pion mass squared is proportional to the light quark masses. So if I change the quark masses, I will change the pion mass significantly. Okay, so I can define these derivatives just to show how sensitive the hadronic mass is to the quark mass. So the pion is, of course, very sensitive to quark masses. If the quark masses were zero, the pion would be massless. The nucleon mass, on the other hand, the nucleon gets most of its mass from confinement. A very small fraction of its mass comes from the quark masses themselves, and we measured this proportionality. We call it sigma pi n. That's the quark mass dependence of the nucleon mass, and that's only about 50 MeV. Which means that compared to quark masses, the nucleon mass is significantly less sensitive to the quark mass. It's only 5%.
QCD measurement.
Yeah, so this you can measure from pion nucleon scattering and from QCD measurements. But this turns out this small sensitivity, 50 MeV sensitivity to the quark mass, will later turn out to be a really important feature when we talk about axion condensation. But overall, the nucleon mass doesn't change very much when you change the quark masses. The heavier mesons, like the vector mesons that appear, they're also not affected by quark masses. Their masses are, again, largely dependent on the confinement and the gluon physics rather than the quark mass physics.
Sorry, are you talking changing masses due to high density or what?
No, I'm just asking the academic question. What if I change the mass?
No, so far you are not specifying.
I'm not specifying what changes the mass. I'm just saying if the mass changes, what would happen? Okay, this is at the moment just an academic question. And there's another meson, which is called the scalar sigma meson, which we think plays a role in nuclear physics. And that is really considered to be like two pions in a coupled channel. So two pions can make a scalar particle, which sometimes is called a sigma meson, and that has some sensitivity to it. So this was a study of great interest about 20 years ago, because people were thinking about fundamental variations of constants in the early universe. People were wondering what if there was something exotic happening in the early universe that changed the quark masses. And 20 years ago, people started worrying about this. But it turns out we really don't know how nuclear forces change when you change the quark mass. We know how the nucleon mass changes. We know how the pion mass changes. But if we ask how does the interaction between two neutrons change, we don't know the answer to that question. And the reason is, you might think, oh, I know that the pion mass changes, and part of the nuclear interaction comes from pion exchange. So if I know how to calculate the force between two nucleons for one value of the pion mass, I can do it for another value. That's easy to do, but there are also these short distance interactions that are written as contact operators in the effective theory. Those we don't know how they depend on quark masses. So the cartoon that you'd see in a textbook on nuclear interactions looks something like this. The force between two nucleons as a function of separation has a very repulsive hard core at short distances and an attractive part where pion exchange and heavier pion exchanges, two pion exchanges, produce attraction. So if we believe that all of this is controlled by pions, making the pion lighter would mean that it gets more attractive. The range of the attractive interaction gets larger. And if the parts of the interaction that are repulsive are insensitive to the quark masses, then the repulsion doesn't change very much. So that was kind of the naive picture in the early days, where they said that, well, let's just worry about the long range part of the force changing when you change the quark masses and leave the short range part alone. And if you make some of those approximations, you can compute, oh, what happens to the deuteron binding energy, the lightest nuclear system that you can bind is the deuteron. And you can see that the deuteron, which is bound by about 2.5 MeV, 2.2 MeV, when the physical value of 138 MeV for the pion mass, as you make the pions lighter or the quarks lighter, the binding energy of deuteron increases rapidly. Okay, so it gets more attractive. So if you had light quarks, you'd end up with more attraction in the deuteron channel, and you'd make deuterons more bound. And in fact, people used these changes in the deuteron binding energy and Big Bang nucleosynthesis to put limits on quark mass variations in the early universe, because it would change the agreement with Big Bang nucleosynthesis. So, there are other quantities like the scattering length of two neutrons. You find that this derivative, which shows how sensitive a low energy observable is to quark masses, you see that it's very sensitive to what happens with the quark masses. So low energy nuclear physics seems quite sensitive to variations in the quark mass, even though the nucleon mass itself is not greatly affected by it. So coming back to the main message of what was missing in the effective theory is the following. So if you think about the leading order term in the nucleon-nucleon interaction, which we wrote down in effective field theory, it's just a contact interaction that has a constant, but this constant has a term that is proportional to mass of the pion squared. And that turns out to be very important. And then there's pion exchange, which is just something you learn in nuclear physics, that two nucleons exchange a pion. This is the potential that the pion exchange generates. So if you change the pion mass here, you'd make this force longer range and more attractive. Now, an effective field theory has a second property, which actually encodes all the short distance physics properly, which says any theory, all effective field theories need to be regulated. So when you try to solve the Schrodinger equation, you have to regulate the momentum integrals. And so you introduce a cutoff, but the answer should be independent of the cutoff. And that renormalization requirement, or the renormalization group equation that says the answers are independent of the cutoff, says that this coefficient is in fact required. D2 must be non-zero, but D2 over C0 squared, this is the leading term that's quark mass independent, that should actually be given by a ratio that's of order 1/4. So this coefficient that introduced quark mass dependence into the short distance part of the nuclear force actually is not small, because the nucleon interaction is very strong, which means that C0 is very strong. And because D2 is proportional to C0 squared, it's telling us that, in fact, this term is very important to include in any calculation of quark mass dependence of nuclear forces. Okay, so this was the part that was known in the 90s, but people hadn't realized that this was also going to imply that in principle, you can measure this D2 by doing lattice QCD calculations of neutron-neutron scattering, where you can change the m pi, because it's a lattice calculation. You can choose any value of the quark masses you want to do, unlike in the real physical world. But it turns out that doing these lattice calculations is not easy. Yes.
What's that? Is HPV? I think I missed. What's the difference between C0 and D2?
So C0 is, this contact is just a representation of short distance parts of the force, right? And there's a piece that is independent of m pi, and there's a piece that depends on m pi. C0 is the piece that's independent of m pi.
You rephrase it by saying that there is some run, maybe it's about saying that there is a running induced by the pion exchange.
Right. So essentially, the pion exchange, if you use a different value of the cutoff, it probes different amounts of the pion exchange at short distances. So the short distance force is sensitive to how much pion exchange is being resolved at a given value of the cutoff.
Okay.
So that's, you can think of it as running of the coupling there. Okay, so the fact that D2 is large as required by renormalization group tells us something else. It tells us that interactions involving two nucleons, which is characterized by D2 times m pi squared, should always come with other terms where D2 m pi squared or 2f pi squared, where two nucleons now couple to two pions. And the reason these sorts of diagrams arise is because chiral symmetry says anytime you see m pi squared in your nuclear physics, the only way m pi squared can enter nuclear physics is in this combination. If you don't write it in this combination, then you will violate chiral symmetry. So if you have a term that has D2 m pi squared, you will have a term that is D2 m pi squared times a product of these pion fields. So which means that a large D2 would imply a large coupling of two pions to two nucleons. Okay, so this part was new, and this is what we had worked on recently. And when we started working on it, we realized that in addition to coupling of two pions to two nucleons with a coefficient that goes like D2 m pi squared, there were two other coefficients that people had thought about many years ago that are also enhanced by the C0 squared. So the bottom line is there are these low energy constants, D2, E2, and F2, which are significantly larger than what people had estimated using Weinberg's treatment of nuclear interactions. So renormalization says that this should be of the order of 1/5 times f pi to the fourth, and f pi is about 92 MeV. Whereas naive dimensional analysis, which is what Weinberg was doing, would suggest that this is 1/λ to the fourth. So there's a factor, a significant factor difference between these. So this could be 100 times more important than initially thought of. So we have to include this.
The energy and free momentum.
So these.
I misheard, or I didn't hear the Q and the omega.
So this is the Q and omega, the energy transfer and momentum transfer to the nucleons in the momentum. So this coupling of two pions to two nucleons gives rise to a 3-nucleon force. And that 3-nucleon force is exactly what's shown here. And this was missed in all previous treatments of nuclear physics and neutron star physics. And because D2 and F2 are significantly larger than what people had expected, we now think that these 3-nucleon forces are an essential ingredient that needs to go into all of the error analysis, whether it be neutron star matter or nuclear matter. And so that's a program that we are now pursuing to figure out exactly how to constrain D2 and F2 using laboratory experiments.
Sorry, but why these larger coefficients do not also signal a lower cutoff where the theory breaks down?
Very good point. So the fact that we had to promote some higher dimension operators to lower dimension just to solve this means that we have to go back and ask, is the error decreasing like we expected? It could well be that when we now compare order by order calculations, that the theory may break down at a smaller scale than previously thought. We don't know. You're absolutely right. It could happen. Maybe we cannot go all the way to twice nuclear density. Maybe we can only go to 1.5 times nuclear density. We don't know the answer to that question, but it's very likely.
But maybe it's not related question, so because there is also analogous vortices with like full pions attention, which would lead to 5 nuclear forces. Are they small?
They will be small. Only those that are coupling, they will be small because they'll be small by whenever you attach more than 2 pions, there's a 1/4 pi F pi suppression that naturally comes. So those diagrams will still be smaller than this. These are large only because the nucleon-nucleon interaction is highly non-perturbative. These are large only because C0 is large. Okay. So if you have 4 pions coupling to 2 nucleons, you'll have a C0 enhancement, but then you'll have another suppression from the fact that you have more pions. So just to bring it on to back into relevance to neutron stars, you can ask, what is the energy as a function of density? And these were the operators, 3 nucleon operators that were relevant in the past. So these were operators that were included in the Weinberg analysis. And when we include these, we don't know what the sizes are. We're just using numbers that would satisfy the renormalization group equation. In principle, they could be significantly larger than the numbers that are currently being used. Okay, so this means that we now have to determine these coefficients D2 and F2 from experiments before we can actually assess what is the error associated with the predictions I was showing in the first part of the talk. So this is ongoing work. Unfortunately, I don't have the final word on it. Bottom line is, for neutron star studies, we may have been underestimating the errors on the equation of state. Because we thought this was the most important 3 nucleon force, and then these coefficients C1 and C3 were well determined by experiment. But now we are saying that these coefficients, which are yet to be determined, could actually make a contribution that's comparable to what was previously considered. And these numbers that have been used in astrophysics, they were very compelling because the errors seemed like they were under control. But if we estimate what is the error in the pressure due to these operators, you can see that they come with very large coefficients. So if they're of natural size, the error could be an order of magnitude larger, which is extremely puzzling. So we really need to include these new forces when we do neutron star equation of state. So that's really the part where we've made progress, but now we've taken a step back and we're looking at the 3 nucleon forces, which are going to play a role in neutron star. So it'll be interesting to see how does that shift the radius measure predictions of the EFT. That's all work in progress. So maybe I have another 5-10 minutes to talk about the stuff that most of you care about, which is axions. And the first part of my talk kind of set up the axion story nicely for you, because as all of you know, the axion was invented to provide a natural explanation for why the theta term in QCD is very small. Essentially, we observe that this term in the QCD Lagrangian has a parameter theta, and that parameter is extremely small. And that can be naturally explained if you promote theta to not a parameter, but a dynamical field. And that dynamical field, if it's energetically favorable for the dynamical field to take on a value of 0, in other words, if that field has a mass, then it would naturally want to be at 0, then that would provide an explanation for why theta is so small. So basically, the introduction of an axion field with a high energy scale associated with the Peccei-Quinn symmetry breaking led to the postulation that theta is in fact proportional to a new field, a pseudoscalar field, axion divided by some new high energy scale. That was an old story. And then the question is, how do we account for this theta term in the QCD theory of low energy? And this was also worked out many, many years ago. They realized that the axion coupling to gluons can be completely eliminated by transferring all of the CP violation in the theta term to the quark mass matrix. Okay, so we know how to do chiral perturbation theory with an arbitrary quark mass matrix. So if I know how to account for theta in the quark mass matrix, then I can put in the axion field into chiral perturbation theory by just changing the quark mass matrix into this new quark mass matrix where the axion field appears explicitly. And so again, this is very old stuff, and you can write down an expression for this matrix Q. And for three flavors, you in fact very quickly realize that the corrections due to the strange quark are irrelevant. And you end up making a prediction for the axion mass, the relationship between the axion mass and the pion mass through the axion decay constant. So all of this is, basically a quick introduction or review of axion physics. And the corresponding energy density of the axion field is given by this expression. And the leading term is Fa squared, Ma squared times theta squared. So of course, this potential is minimized if theta equals 0, and that solves the axion, the small theta problem. The part which is also appreciated in the past is that when you change the quark mass matrix, it changes the pion masses because the pion masses depend on the quark mass matrix. You can calculate how the pion mass changes when you change theta. And you find that when theta goes from 0 to pi, the quark mass decreases significantly. So the ratio of the quark mass squared is now 1/3. So at theta equals pi, the pion is significantly lighter than at theta equals 0. And because we know how the nucleon mass depends on the quark mass or on the pion mass, we also see that the nucleon mass also decreases with the pion mass. So nucleon mass goes from about 940 MeV to about 900 MeV if you go from theta equals 0 to theta equals pi. So that should already lead you to ask, I know that theta wants to be 0 in the vacuum, but what about theta when you have a lot of nucleons? Because when I have theta equals pi, each nucleon weighs a lot less. So I'm going to gain energy. I'm going to gain about 30 or 40 MeV of energy by just turning on theta. And in fact, that's what happens. So if you ignore interactions between neutrons, you find that if you have a source of baryons, the free energy as a function of theta, so for very small baryon chemical potential or for very small densities, the theta still wants to be 0. But as you go to higher chemical potentials, this is what happens inside a neutron star. So as you go inside a neutron star, the baryon chemical potential keeps increasing. And at some density of about 2.5 times nuclear density, you in fact find that there's a first order phase transition where theta wants to go from 0 to a new ground state at theta equals pi. So if neutrons were not interacting with each other, we can very safely conclude that axion condensation is happening inside a neutron star because neutron stars have densities that are significantly larger than 2.5 times nuclear density. So in fact, when I first thought about this or read about this, I realized, this is pretty amazing that, it's a prediction of the QCD axion, and the only approximation we are making is that we are ignoring interactions between neutrons and protons. And that can have two sides. If I change the meson masses, if I make the meson masses lighter and the interaction energy decreases with decreasing pion mass, that means interactions favor condensation. So in the absence of interactions, if the condensation was happening at 2.6 times nuclear density, and if the interaction got more attractive when the pions got lighter, then we would be forced to conclude that the critical density for condensation should be less than 2.6 saturation. So the only way axion condensation can be prevented in the neutron star is if this was not true.
How come it doesn't depend on this coupling constant F? Because QCD axion can come with arbitrary F, and yet
This is independent of F. This is because theta is A over F.
Right.
And when you have theta equals pi, if you change value of F, it means that you just have
so
many
F
more
cancels.
axions. So this condensation is independent of the value of F. It will happen for any value of F. Because it's the ratio of A over Fa. So now the question is, do nuclear interactions decrease when I decrease the pion mass? And unfortunately, I don't have a final answer for it. We're working hard to figure out if this is the case. So the question we're asking is, if I go to high density nuclear matter and I calculate the interaction energy at an arbitrary value of m pi, and I subtract it from the physical value of m pi, is this number positive or negative? If this number is negative everywhere, then condensation happens below 2.5 times nuclear density. If it's higher, then it may not happen at all. And our calculations, which are actually led by a young faculty member at Ohio, Christian Drischler, using chiral effective theory, predicts these are the results he obtains when he changes the pion mass in his setup in chiral effective theory. The first thing he notices is that if you just do a leading order calculation, which is like a mean field Hartree-Fock calculation, in fact, the energy increases with decreasing pion mass. So this would have suggested that maybe axion condensation is suppressed by lowering the pion mass by nuclear interactions. But actually, when you go to second and third order in this calculation, which is called many body perturbation theory, we find that that trend reverses, and one finds that the interaction energy becomes negative, which means it is actually favoring condensation of axions. But at the moment, we are not willing to make a firm prediction, because if you do the same calculation at two different values of the cutoff of this effective theory, a good test of whether or not you're accounting for all of the pion mass in short distance physics is to see if there's any cutoff dependence. So if you compare this curve to the curve I showed you earlier, you see that there is significant cutoff dependence. We still see the same trends, but the actual numbers are changing. So at this value of the cutoff, you get a lot of attraction at small values of the pion mass. But at this cutoff, you don't get as much attraction. So we are now trying to understand whether there are missing terms in the effective theory so that we can account for this cutoff dependence. But both these calculations suggest that interactions may be getting a little more attractive when you make the pions lighter. And if that remains robust, then it would. Then the implication is that axions, the QCD axion, would condense inside a neutron star. So ultimately, we think about a phase diagram for QCD axions. So as a function of density, you would calculate the energy difference between a hypothetical state with pions of 80 MeV and the physical pion mass. And if you're in this region, you have the theta equals 0, a state of matter with no axion condensation. Or if you're in this region, you'll be in the theta equals pi region, where axion will have condensed maximally. And theta equals 0 and theta equals pi are both CP conserving. There's no unusual properties there with respect to CP violation.
Like you should bring spontaneous CP at equal pi.
But spontaneous CP breaking happens only for special cases of quark masses. If your quark up and down quark masses are different, then this dash-in phase of spontaneous CP violation does not happen for physical values of pion mass. But for special values of quark masses, we can have CP violation and theta equals pi. So we can chat about that more later, but the bottom line is if condensation happens at densities around twice nuclear density, the the neutron star may look like this. This is a student of mine, Mia. She's the one who's constructed all these neutron stars with non-zero theta in their interiors. And we think that, we're now looking for observable signatures of having a theta equals pi phase deep inside the neutron star in some region of order a few kilometers. Okay. So in this region, when you go from theta equals pi to theta equals 0, there's a domain wall, and the extent of that domain wall here is shown to be very small, but that domain wall can be large, can be as large as a kilometer if the axion mass is very small. Okay. So in that domain wall, you can have CP violation. Okay? And we are looking at whether there's some interesting physical implications of having CP violation in this domain wall region. But ultimately, what we'd like to do is define neutron stars with non-zero theta in their interiors and figure out how different would they look from an electromagnetic or a gravitational observable. So just to kind of wrap things up, our recent work has shown that three nucleon forces, which are very important for neutron stars, now have important contributions from operators that are enhanced compared to earlier studies, and we are trying to figure out what its implications are. And these operators arose because we wanted to really understand the quark mass dependence of nucleon-nucleon interactions. And chiral symmetry said that, whenever you have quark mass dependent interactions, it also induces new interactions with pions. And this quark mass dependence of pions is key to understanding axion condensation. So the question of, what is the quark mass dependence of nuclear interactions led us to discover some new three-body forces, but it also is showing up as a key ingredient in asking the question of, do axions condense in neutron stars? Finally, I think it's going to be interesting when we have more data on neutron stars to see, what sort of properties of QCD they can reveal and what calculations we can do to inform astrophysics. Thank you very much for your patience. I just pointed in the general direction. You go.
All right. So for like if there are these domain walls for neutron star mergers, do you expect there would be some effects because maybe the pion mass is lighter in the inner region and then heavier in the outer region? So there be any effects in the remnants or?
Good question. The honest answer is we don't know. People have thought about extremely light axions, which would condense not at 2 times nuclear density, but would condense at very low density. This is work by Jim Wong and Anson Hook. In that case, the axion leaks out of the neutron star. So the axion field goes out of the neutron star. And there, people, of course, that would have an effect when you have 2 neutron stars 100 kilometers apart and they have overlapping axion clouds. Those limits are all well developed in the literature and they exclude a lot of that parameter space. My focus is really on the QCD axion, which is not going to leak out of the neutron star, it's going to be contained in. And even though the pion gets lighter because of its interaction with theta, we don't know how because the pion interaction with the nucleons increases the pion mass. So there's a lot more work to be done before we can go to the observables.
Can you potentially, at least for me, it would be most interesting, can you potentially rule out axions? You see a neutron star by its very radius and mass, you say no axions, forget it.
Yeah, so I think this is the real
power. Looking for bounds on axions, whatever, and then you come and you say, forget it.
I think that's the real power of this treatment. The first powerful nature of this constraint is it's independent of FA. The second powerful nature of this is we only need to answer one question. Do nuclear forces get more attractive or less attractive when the pion mass decreases? If it gets less attractive, then we can't say anything. But if we can conclude that in fact nuclear forces get more attractive when you decrease the pion mass.
You're saying you cannot compute yet.
Not yet, but I think the framework exists. I think we can make a kind of a very useful probabilistic statement saying within the EFT errors, 50% probability the axion will condense. And if it condenses, then we can look for observable signatures. So Yeah, I mean, the question, there are still some questions, is the EFT going to be useful at these densities?
So say it does condense and there is this domain wall at 5 kilometer depth or something like this. Would that be observable already? If, not through CP violation or something like this, but just the stress energy contribution?
No, that would not be easy to do, you know, you look for mass radius effects in the mass
Yeah,
radius.
yeah.
There you will have to make very fine radius measurements. Because you will have to measure the impact of a small domain wall, because the stress energy there is not overwhelming the stress energy of the
But
nuclear
it's
matter itself.
it's comparable, right? Or
It-
it's not
it's-
orders of magnitude smaller.
It's not orders of magnitude, it's comparable. So it's F pi squared times M pi squared. That's a typical
Correct.
scale of the energy density. That's like maybe 20% of the nuclear energy density. But 20% effects in one location of the neutron star is not, you cannot deduce
I
it
see.
unless
It's
you
a
have very
small
precise
expansion.
measurements.
I see.
Could you produce a lot of axions in a merger? There's this condensation.
So the axion, okay, so there's the condensed axion, and now you want to generate thermal axions on top of that. So the axion mass in the condensed phase is actually a little heavier. So but it'll still be small compared to the temperature. You'll make a lot of axions, thermal axions that will come out of the merger. Is that what you're talking about?
Yeah, that or just something non-regenerative that happens during the merger. I mean, for example,
Oh.
as it gets eaten by a black hole and the neutron star is disrupted. And it's
Like you spit lots of axions during
Yeah.
merger.
the
Is
domain
that
wall.
what you were asking?
Yeah, that's what I was.
Yeah, so the axions that will make it out of the high density regions will be thermally produced, right? I mean, if you can change the thermal production if you already have a BEC of axions there. But the axions that are going to be coming out are not going to be in the condensed phase. They'll be just like your vacuum axions.
Yeah.
Yeah, there could be a different rate of production in these axion condensers.
No, but seriously, it would be like neutrino emission. You lose a lot of energy. Even if you don't see those axions, if you lose like whatever, 90% of energy, it
no,
will
no.
be a disaster.
In fact, that is used from 1987A, the supernova 1987A constraint on axions, which is one of the most powerful constraints on axions, comes from exactly the argument you're making. We saw the neutrinos. If you have a very small value of Fa, you would make so many axions that the neutron star, which is born in a supernova, cools by axion emission, not by neutrino emission. So the fact that we saw neutrinos already puts a bound on the axions, and that is already a good bound.
Another question, or maybe what you had in mind is that you would see it in the gravitational wave signal.
Yeah, so if there is something unusual about the post-merger dynamics, right? You start seeing the interior of the neutron stars only after they touch and they form this complicated object.
But if that's cooling really fast, it would have all sorts of impact.
True, but unfortunately, it doesn't last very long, right? Unless we make if after the merger, you produce a stable object that can last for days or hours, then you'll be sensitive to cooling. But if you had an object, most often these mergers collapse to a black hole on timescales of hundreds of milliseconds. That is too short for cooling. The cooling timescale is hours or days for these objects.
But also so far, you don't even know if this condensate is there.
Yeah, we don't know if that's there.
Right, so-
You know, we'll have to do simulations with the condensate to see if it has any observable impact on the gravitational waves. But it's all nuclear physics. It's not exotic physics. I mean, that's the main part I want to emphasize. This is stuff that does not introduce uncontrolled new particles or uncontrolled new approximations. It's all within the framework of low energy effective theory. And that's why I find that this may be a useful direction to pursue.
There are no more
Thank you
questions.
so
but
much.
thank you.